So far we've been dealing with fairly simple examples of data just in a comma-separated value format or tab-separated value, whatever it might be. And that works fine when you're dealing with data that can be represented compactly on one line at a time. So if you just have really simple data where you're just having columns of information, and it's not really more complex than that, where you don't have any sort of substructure, fine. But in the real world, you'll probably have more complex structure to your data. And the compression and handling and splitting up of that data becomes a problem. And to solve that problem, we have a wide variety of different file formats that you'll see in the world of big data. So let's go through and talk about what some of them are and how they're used. First of all, we have the human-readable non-binary formats, and non-binary is kind of a loaded term these days, but we just mean that literally. It's in a text format that's human-readable, as opposed to being in a binary format that is machine-readable. And the two big ones, apart from CSV files and things like that, are JSON and XML. JSON seems to be winning the battle. It is a very compact representation and very extensible. So we can represent things like arrays or substructures and subfields like this example here. You can see that we have a properties field that contains a first name and a last name and an age, which furthermore contains more information, the description of the field, the type of that field, the minimum value of that field. So you can encode pretty much anything you can imagine in the JSON format. The big advantage, though, is that it's very compact. It's not very rigid. It can have a lot of flexibility in what you put into it. And for that reason, it's very popular for being the format that people send data in over the wire, especially if you're going to be building it within the context of a website. Since you can just read this data in JavaScript, it's very easy to unpack it and display that on a website just using JavaScript. XML, in contrast, is an older format. This kind of goes back to the Microsoft days. The thing with XML is that it's extremely powerful, but it does require a document object model. And that really provides a lot of rigid structure on what can be in the XML file. So there's a lot of features in XML to validate the file itself and make sure that you're not violating any of the rules or the structure that you've defined for that file. The downside is that it makes these files relatively large, and you can't just decompress them and access its data from JavaScript. You actually need to have an XML parsing library that can be a pretty heavyweight thing. So it takes longer to decode an XML file, but it is more rigid, and it does force you into the format that you declare in that document object model. Again, JSON, I see that a whole lot more than XML these days. But if you're dealing with massive data sets, you might not see either of these formats for a couple of reasons. One is that text data is not a very efficient way of representing and storing information, right? So why should I represent sub-menu item and that little string there all the time? Why should I type out the word properties and store that over and over and over again for no good reason? It's only useful if you have humans looking at the data and trying to understand that file, looking at it directly. The other big issue with non-binary formats is how do you split them? So often when we're dealing with big data systems, we're going to be splitting up our input files and distributing them out to many different servers on a cluster in parallel. How do I do that with JSON or XML? If I just arbitrarily cut this data in half, I might be in the middle of that properties block there in the JSON example, or I might be in the middle of one of those submenu items blocks in the XML example. Without that context surrounding each line, I can't really interpret that data. So splitting this data becomes very complex. You need to have a lot of knowledge about the file itself and its larger context to know where it's safe to split that. So JSON and XML are great if you just need to deal with smaller data sets and you need to understand it by just looking at the file. But when you get into the world of big data, they tend to be less practical because they cannot be split easily and they're not very compact or efficient. And that's why we have things like binary formats instead. So there's two different classes of binary formats out there, column-oriented and row-oriented. Let's start with column-oriented. So why would we have a column-oriented data format where we're actually writing out data based on the columns instead of the rows that are coming in? This seems kind of backwards to how you normally represent data, right? So instead of representing a row of information that contains all of the fields associated with one thing, instead in a column-oriented format, we're writing out the individual columns of data. And this makes it much more efficient when you're doing queries that are based on columns. So even though it seems backwards conceptually, by storing data in a column-oriented format, it means that queries that are only accessing certain columns or certain fields of your data can be done much more quickly because it doesn't need to read all those other columns at all. Imagine doing a query across a data set that has a lot of different fields and you don't even need most of them for the query you're executing. I'd have to go through every single row of data, picking up all that data that I don't care about just to query it based on the columns that I do care about. So for read-heavy applications where you're doing queries just on specific columns, the column-oriented formats are a better choice. Now there are two main types of column-oriented binary formats. One is ORC, which stands for Optimized Row Columnar, and this is mostly a Hadoop thing. It was developed as part of Hadoop, and you'll see it mostly used within the context of Hive or HDFS. The other one is Parquet, and Parquet kind of has its derivatives from the world of Google and Cloudera, and more modern systems like Apache Spark and newer big data or data engineering systems tend to lean toward Parquet as a column-oriented format. You'll see that a lot in the world of AWS data engineering as well. And again, the main advantage here, apart from being very efficient for reading and querying, if you're only querying certain columns, is that it can also be very easily split. So these ORC and Parquet formats can both be split arbitrarily, where we can just split up large files of big data and send off chunks of it to different servers for processing in parallel. That's very easy to do with both ORC and Parquet. Finally, let's talk about the binary row-oriented formats. So with a row-oriented format, it's more like what you're expecting. Imagine sort of a binary version of a CSV file, basically. And these are appropriate for write-heavy applications. So if you are just loading large data sets where you need to load every column of every row all at once, there's really no point in the complexity of column-oriented storage in that case, right? Because we are actually loading entire rows of information. So when I'm just trying to push data from one place to another, a binary row-oriented format might be a better choice. Now, I kind of described it as a binary version of a CSV. That's not really fair because it can handle more complex structures of data there as well. So let's talk about Avro, for example. You can define a schema in Avro using JSON or an IDL format. So you're not just limited to a very simple, fields in a row sort of a format there. You can have more complex structures there where a field could contain further subfields within it and so on and so forth. Avro, in addition to being popular in the world of Hadoop, is also popular in the world of Kafka. We haven't talked about Kafka yet, but that is a popular data streaming package. So a lot of the open source data streaming technologies will work very efficiently with the Avro format. And again, the use case of data streaming is just pushing data from one place to another really quickly, really in real time, right? So in that case, we're pushing entire rows across, and a binary row-oriented format would be a good choice. Another one worth talking about is protobuf, and this is basically something that Google defined, and it's their format for data interchange internally. They describe protobuf as like XML, but better, more compact, a little bit simpler. So same idea though, it's still a binary-oriented format where you can have complex structure associated with it, but typically you'll see protobuf in the context of Google-derived systems. So for example, if you're loading up a big data set to do machine learning, and whoever's doing that machine learning is using a Google system like TensorFlow, there's a pretty good chance you'll be using protobuf to do that. I've also seen protobuf used in Apache Spark as well for its machine learning library. So usually I'm seeing protobuf in the context of machine learning, but there's no reason not to use it in other situations where you might need to load large amounts of data if your tools support it. So that's data formats in a nutshell. Again, in this course, we're going to keep it simple and stick with things like CSV files just because it's easier for you to wrap your head around that as a beginner. But keep these other formats in mind because in the real world, you'll need to know when to use these different formats for different situations. And by switching to these binary formats, you can achieve great speed ups in processing time and in query time as opposed to using text-oriented, human-readable, non-binary formats.